I welcome you to this class of econometric methods. I am Dr. Muhammad Imdadul Haq, an associate professor in the Department of Economics of Aligarh Muslim University. We were in the discussion on autocorrelation. We have seen what are the effects of autocorrelation. We have seen what are the reasons why autocorrelations occur. We have studied the types of autocorrelation. Then we have discussed how to identify, that is the detection of autocorrelation, and in that we have studied Durbin-Watson statistics. One issue with Durbin-Watson statistics is that you cannot work if the autocorrelation is of second degree. Now, if that is the case, that your autocorrelation is of second degree, then we have to go for Bush-Godfrey test. This test you can accommodate even if your autocorrelation is of second degree. Now, let us quickly go through the process of Bush-Godfrey test. Herein, see your y. So, we take with the model y is equal to beta naught plus beta 1 x1 plus beta 2 x2, and likewise you extend it, and e is the error over there. Then once you have done the estimation, then you calculate the residuals. In residuals, calculation of residuals means actual y minus the estimated y. Then we augment the data with lags, meaning thereby that we create lagged versions of the residuals. This involves creating additional columns in the data set representing the residuals at different lags. The number of lags depend on the order of serial correlation you want to test. Say for example, if you want to test for first order serial correlation, create one lagged version of the residuals. If you want to test for second order serial correlation, create two lagged versions, and so on. Then we fit the auxiliary regression, that is, we regress the residuals on their lagged values and if there are any other exogenous variables. So you estimate this equation, that is Et is equal to beta naught plus beta 1 Et minus 1 plus beta 2 Et minus 2. This will be Et, just a second, Et minus 1, Et minus 2, and then what we do, we calculate the test statistics. Once this regression is estimated, then we calculate the test statistics. In the test statistics, it is the formula is n minus p. In the test statistics, the formula is n minus p, where this n is your sample size, p is the number of lagged residuals included in the auxiliary regression, whether you have included 2 or 3 or likewise. Now, so n minus p multiplied by r square. R square is your coefficient determination, and this is done through the chi-square test, and we assume that this is going to have a chi-square distribution with p degrees of freedom. So once we have calculated this Bush-Godfrey statistics by this formula n minus p multiplied by r square, now if the test statistics exceeds the critical value, you reject the null hypothesis of no serial correlation. Your chi-square distribution is basically a right tail test, and what happens if your test is your Bush-Godfrey test falls over here, it means you reject the null hypothesis of no serial correlation. That means you get that there is serial correlation, there is serial or autocorrelation, and if the test statistics fall over here, then here it is no autocorrelation. So this method is, and you will find it with all the softwares nowadays where you are doing any time series analysis. So instead of Durbin-Watson, we go for Bush-Godfrey test to detect the presence of autocorrelation. Now we have seen what is the reason why it happens, what happens because of autocorrelation, what are the types of autocorrelation, how to identify the autocorrelation. Now we come on to the next thing, that is what is the solution for it. See, it basically depends on the factor which is causing this autocorrelation. For example, if the autocorrelation is because of you have excluded an important variable, then, and it is, if you have excluded an important variable, it is sitting over there in the error term, so there is a systematic variation in the error term, it means there is an autocorrelation problem. So the solution is include that in the variable. You have misspecified a model. You have taken you have a relationship of which is like this. You have a relationship which is like this, but in reality what you have done, you have fitted a straight line. Obviously, again the impact of this curve, that additional variable x square, and that is square term, it is sitting in the error term. So what is the solution? You specify it correctly, that's it. And suppose if, what is the next one? If it's not because of any of these two reasons, that is it's not because of variable exclusion or not because of misspecification, in that case now you have to go for the next thing, that is transformation of the model. See, while you go for transformation of a model, basically one thing we assume here, that we must know the form of autocorrelation, whether it is of first degree or second degree, or we must have the estimate of p. If these things are known, then we can go for it, and we will see at a later date how to get the values of the p. We will see it just in a few minutes. So say we have a model yt is equal to alpha plus beta xt, and say we assume that we assume a first order serial correlation, that is ut is equal to rho ut minus 1 plus vt, and say we know the value of rho. So what we do, we transform the model as we will be transforming the model by taking say one period lag first. So yt is, this model is written as yt minus 1 plus alpha plus beta xt minus 1 plus ut minus 1. Now we multiply this with rho. So it becomes rho yt minus 1 is equal to rho alpha plus rho beta xt minus 1 plus rho ut minus 1. Then our original equation was yt is equal to alpha plus beta xt plus mu. Now this minus this, original equation, this is equation number 1, this minus this, you get, you do the minus, that is the term which we get is alpha minus rho alpha plus beta xt minus rho beta xt minus 1 plus mu t minus rho mu t minus 1. Now if we take here alpha common, here beta common, and this term we denote it by Vt. So this we can finally write as y asterisk is equal to alpha asterisk plus beta, means this you denote it by x asterisk, and this term you denote it by and this entire term you denote it by alpha asterisk. So now this is what you can denote it finally. Now suppose we take another case where we know that we are going for a second order autocorrelation. Now here the form of autocorrelation is ut is equal to mu t is equal to rho 1 mu t minus 1 plus rho 2 mu t minus 2 plus vt. So now we transform this equation, our original equation, into yt minus 1, we take one period lag over here, and then we next transform it into yt minus 2, we take a lag of 2 periods over here. This equation B we multiply by rho 1 and we get the resultant as rho 1 alpha plus rho 1 beta xt minus 1 plus rho 1 vt minus 1, and the second equation C we multiply by rho 2. So this gives rho 2 alpha plus rho 2 beta xt minus 2 plus rho 2 vt minus 2. Now we subtract the first equation, that is yt We subtract yt minus rho 1 yt minus 1 minus rho 2 yt minus 2. We subtract the two of the equations. So we get the first term as alpha minus rho 1 alpha minus rho 2 alpha, plus the second term, that is beta xt minus rho 1 beta xt minus 1 minus rho 2 beta xt minus 2, plus the third term v1 minus rho 1 vt minus 1 vt minus rho 1 vt minus 1 minus rho 2 vt minus 2. Now what we do, we take this, we assume that yt minus rho 1 yt minus 1 minus rho 2 yt minus 2 means this term we assume it to be yt asterisk. Then this term we assume it to be alpha asterisk. This term from here and this over here, this term we assume it to be beta asterisk xt asterisk, and this last error term we assume it to be vt asterisk. So finally we can write the final equation. This same equation can be written as, assuming these three things, it can be written as yt asterisk is equal to alpha asterisk plus beta xt asterisk plus vt asterisk. See, earlier equation was yt is equal to alpha plus beta xt plus ut. Now we had an autocorrelation of there with an order ut is equal to rho ut minus 1 plus vt plus, but this equation which we are having over here, now this equation is free from the problem of autocorrelation. So this is one of the solutions. Now only thing is you need to know which type of autocorrelation is there, it's the first order or second order, and you need the value of rho. We will see how to get the value of rho. Now, so in research, in applied research particularly, when there is a chance of a presence of autocorrelation, an estimate has to be made about the value of rho. Many a times, as a priori information, many a times it is assumed to be 1. The beauty of this, if you make it 1, is the model becomes very simple. You simply assume that the value of rho is equal to 1. Next thing, by using your information, by using your dw statistics, d asterisk is equal to 1 minus rho, and from this you estimate the value of rho hat summation et multiplied by et minus 1 divided by summation e squared et minus 1 square. So now this is again a way to know the value of rho. Now we move to another method that is called as Cochrane or Cut iterative method. In this method, it involves a gradual approximation to estimate this autocorrelation function. Now, so we see what is the process. So you have a model yt is equal to b0 plus b1 x1t plus et. Now you apply OLS, so you can estimate the equation. So estimated equation is y hat is equal to b0 hat plus b1 hat x1t. Now you want to find the residual. What is E? E is equal to nothing by actual y minus the estimated y. So now you can calculate the residual likewise. E is equal to y minus y hat. Y hat you have just now seen, and the value of rho hat is you can calculate the value of rho hat by doing the calculation over here, that is summation et minus 1 divided by summation et minus 1 square. Now once you have done, from there you get, from this value of rho which you are getting over here, this means this is very it's not complicated. You have x, you have y, and then you calculate the value of b1, you calculate the value of b0. You know the formula of b1, that is summation x minus x bar y minus y bar divided by summation x minus x bar square. b0 you know y bar minus b1 x bar. Now once you have done, then you estimate y hat, then what you do, you get your value of E, which is nothing but y minus y hat. Now this is your ET. Now this is your ET, then you estimate a column of ET minus 1. This is nothing but, suppose your ET was 5, 6, 10, 20, 25. Then ET minus 1, this 5 you will write at a 1 period lag. This comes 6 over here, this comes 10 over here, this comes 20. Then what you have? ET minus 1. So likewise, you do the calculation, then you do the multiplication of these two terms. That is, this is 30 and this is 60. Likewise, you do the summation of it. Then also it is asking for ET square. ET square is nothing but 5 into 5, 25, 6 into 6, 36, and you do the summation of it. So likewise, you are getting the value over here. Now, you use that rho hat which you have got from there, you use it in this equation. That is, what you do, this was your original equation. This was your original equation, yt is equal to b naught plus beta 1 xt plus ut. Then you take 1 period lag, yt minus 1 is equal to beta naught plus beta 1 xt minus 1. Then again you take it 1 period, then you multiply it by rho. So it becomes rho hat yt minus 1 is equal to rho hat beta naught plus rho hat beta 1 xt minus 1 plus rho 2 ut. Then this equation minus this equation. Upon doing that, it can be written as beta naught 1 minus rho hat and with bracket plus beta 1 bracket open xt minus rho hat xt minus 1 bracket close plus u2 asterisk. So here now your beta double hat is the estimate of and beta 1 double hat is the estimate of this. Now what we can do is, you get beta naught hat, we again do the same process, we do the calculation of ET double hat and we get, we do YT minus the value over this Y double hat, then from this we again calculate the value of rho double hat. Now you get get a value of rho double hat. You can again repeat this process. You can go on repeating this process again and again, and till the value of rho hat it converges. Now many researchers, they stop at the second process also, but it can go on extending. So normally they stop at the second process. But the thing is, when we say that the value of rho hat converges in this Cochrane-Orcutt method, it means that as the iterative procedure of the estimation algorithm progresses, the value of rho hat stabilizes or converges to a certain value. This is an indication that the algorithm has reached a stable estimate of the coefficient of autocorrelation in the data. In this method, the value of rho hat should converge to ideally what is the true coefficient of autocorrelation in the data. However, in practice, this true value is typically unknown since the method is used precisely because autocorrelation is present and needs to be estimated. Therefore, the value to which rho hat converges represents the estimated coefficient of autocorrelation. Ideally, this estimate should be close to the true coefficient of autocorrelation in the underlying this data generating process. The iterative process of this Cochrane-Orcutt method aims to refine this estimate, iterating until the value of rho hat stabilizes or converges, this indicating that the estimation has reached a satisfactory level. So this was the method of Cochrane-Orcutt estimation of rho hat. Thank you.